So in this video we're going to talk about chemical formulas and how we generate chemical formulas and what those formulas kind of tell us. So when we're looking at molecular formulas are going to give us the actual numbers and types of atoms in a molecule. Alright, let's look at some examples here. So H2O, water, means I got 2 hydrogens, 1 oxygen. CO2, 1 carbon, 2 oxygens. CO, 1 carbon, 1 oxygen. CH4, 1 carbon, 4 hydrogens. H2O2, 2 hydrogens, 2 oxygen atoms combined together. O2, 2 oxygen atoms. O3, which is 3 oxygen atoms. C2H4, I got 2 carbon atoms, 4 hydrogen atoms. C6H12O6, 6 carbon atoms, 12 hydrogen atoms, 6 oxygen atoms. C6H5NO2, 6 carbon atoms, 5 hydrogen atoms, 1 nitrogen atom, 2 oxygen atoms. So I think you get the basic idea. These are molecular formulas. What we see is the actual numbers and types of atoms in the molecule. Now, a different type of formula is something called an empirical formula. An empirical formula is going to give the relative numbers and types of atoms in a molecule. So an empirical formula is also going to give us the lowest whole number ratio of the atoms. So let's look at some examples of this. Well, H2O, 2 hydrogens to 1 oxygen, that's a 2 to 1 ratio. That's the smallest whole number ratio we can get. If we go any smaller, we'd end up with H1O.5. We can't do that. So CO2, it's a 1 to 2 ratio. CO, it's a 1 to 1 ratio. CH4, it's a 1 to 4 ratio. HO is a 1 to 1 ratio. So I think you get the idea. When we look at O2, they can't have a ratio there. It's just 2. O3 can't have a ratio. CH2 would be a 1 to 2 ratio. CH2O would be a 1 to 2 to 1 ratio. And C6H5NO2 would be a 6 to 5 to 1 to 2 ratio. Now let's compare these two to see how they relate to each other. So I've got empirical formula on the left, molecular formula on the right. Remember, empirical formula, the lowest whole number ratio, gives us the relative amount of atoms. Molecular formula gives us the actual number of atoms. So I could look at H2O. Well, if I look at a ratio, H2O, that's a molecular formula as well. If I have HO for an empirical formula, I could have H2O2 for a molecular formula. Remember, empirical formula, the lowest whole number ratio. Molecular formula gives us the actual number of things. So if the molecular formula is H2O2, I can divide both those by 2 to get the empirical formula. Right? If my empirical formula is CH2, I can get a lot of different molecular formulas from that empirical formula. I can get C2H4. If I multiply everything by 2, I can get C3H6. If I multiply that CH2 by 3, I can get C4H8 if I multiply those numbers by 4. So molecular formula shows us the actual number of atoms. Empirical formula, smallest whole number ratio. I've got CH2O. Molecular formulas I can get would be C3H6O3 or C6H12O6. Okay, C6H5NO2. I can get C6H5NO2. Those are molecular formulas, empirical formulas. So sometimes the molecular formula is the same as the empirical formula. Sometimes the molecular formula has a higher values than what the empirical formula is. Okay, you need to be able to distinguish between those. All right, what we're going to look at next is how we get these empirical formulas. And remember, with these formulas, it's showing us what types of elements are combined. We get, for the formula, the elemental symbols based upon the periodic table for the different elements. And don't forget, off the periodic table, we're also going to be able to get the molar masses for those specific elements. It's going to be important. So when determining empirical formulas, we want to get the smallest whole number ratio of a compound. First, though, we need to understand something called mass percent. Mass percent of a compound is going to take the mass of an element in that compound divided by the total mass of the compound and then multiplying it by 100%. Now, one thing to keep in mind whenever you're doing these types of calculations, if you've got a chemical formula and you're going to calculate mass percents from a chemical formula, the easiest thing to do is to assume you have 1 mole of the compound. That way, the total mass of the compound is equal to molar mass. So let's look at an example calculation of this. What is the mass percent of each element in H2SO4? Well, first thing we need to have is the molar mass. We want the molar mass of H2SO4. Well, if you remember back to doing those calculations, I have 1 mole of H2SO4. 1 mole of H2SO4 is equal to 2 moles of hydrogen. Then 1 mole of hydrogen is equal to 1.008 grams of hydrogen. That's the molar mass of hydrogen. Gives me a total of the 2.016 grams of hydrogen. That's the mass of hydrogen in 1 mole of H2SO4. And now remember, I'm doing molar mass, so I got to do that for the sulfur. I've got to do that for the oxygen. Add them all up, I get the 98.09 grams. So my molar mass is 98.09 grams of H2SO4 per 1 mole of H2SO4. Okay, you've seen that before. That's just a quick review of molar mass, but you need to know how to calculate molar mass. So, going back to the original question, what's the mass percent of each element in H2SO4? Well, we now know our molar mass is 98.09 grams per mole. In order to calculate the percent of hydrogen, we want to know the mass of hydrogen in 1 mole of H2SO4. We're going to divide that by the molar mass of H2SO4. Remember, we're assuming that 1 mole of H2SO4. And then we're going to multiply it by 100%. So what's the mass of hydrogen in 1 mole of H2SO4? Well, we start with our 1 mole of H2SO4. 1 mole of H2SO4 to 2 moles of hydrogen. 1 mole of hydrogen to 1.008 grams of hydrogen. Gives us our 2.016 grams of hydrogen. We've already done that calculation to get the molar mass. So now all we need to do is take that 2.016 grams of hydrogen divided by the 98.09 grams of H2SO4, multiply by 100%, and we get 2.055%. Okay, so we've got that percent hydrogen. Let's look at the other elements in the H2SO4. Percent sulfur, we take the 32.07 grams of sulfur divided by 98.09 grams of H2SO4 times 100%. Percent oxygen, we'd have 64 grams of oxygen divided by 98.09 grams of H2SO4. In looking at all of these, one thing to think about is when we look at these percentages, those are the only things in that H2SO4, so why don't these percentages all add up to 100%? Well, that goes back to significant figures, that goes back to rounding errors. That's why overall we don't end up with a 100% mass percent, even though we should. Okay, that's always going to be a problem. We're always going to have that issue of rounding error. So that's how we calculate mass percent given a formula. In order to determine empirical formulas, though, typically what we do is we get mass percents by running experiments, and then from those mass percents, we can actually go through this calculation kind of backwards to get an actual empirical formula. And that's what we're going to look at. So we're going to determine empirical formulas from mass percents. So let's say we run some experiments, and typically we can do like mass spectroscopy. That's the name of the instrument we can use to determine mass percents of elements. There's other methods we can do as well. Let's say we take a compound, we run this analysis, and we end up with 55.3% potassium, 14.6% phosphorus, and 30.1% oxygen. Those are our mass percents of our elements in our compound. Now from those mass percents, we want to get an empirical formula. So we're going to have to work that process we just did before backwards. If we assume we have 100 grams of the sample of interest, that's going to help us get masses of these elements. Well, if I have 100 grams of my sample and I know 55.3% of it's going to be potassium, well then I know I have 55.3 grams of potassium. If I know 14.6% is phosphorus, I know I have 14.6 grams of phosphorus. If 30.1% is oxygen, then I know I have 30.1 grams of oxygen. So assuming that 100 grams of sample is just a simple way of us getting those starting masses. We can just use the percentages that we have. Okay, but pay attention to writing down those units because they're no longer percentages, they're the grams. All right, next we need to determine the moles of each. Remember, we're looking at an empirical formula. The empirical formula is going to give us ratios of the moles of these things to each other. That's what's going to be in a formula. So how do we get moles from a mass? Well, if we look at potassium, I have 55.3 grams of potassium. If I divide by potassium's molar mass, So I put grams of potassium on bottom, moles of potassium on top to make sure my units cancel. I get 1.414 moles of potassium. Do the same thing with the phosphorus. I can do the same thing with the oxygen. So all I'm doing is taking those masses, converting to moles. Now, keep in mind, with the empirical formula, we want the smallest whole number ratio. So in order to get that, we're going to have to divide everything by the smallest number of moles. If you divide everything by the smallest number of moles, that means at least one of those values is going to be a 1, which is the smallest whole number we can get. So let's look at the potassium. Well, the smallest number of moles out of all three of those was the phosphorus. So if I take the 1.41 moles of potassium divided by the 0.471 moles of phosphorus, I get 3. For my phosphorus, if I take the 0.471 moles of phosphorus divided by the 0.471 moles of phosphorus, I get 1. Now, keep in mind we're getting these ratios set up. So these units technically aren't going to cancel when we divide out. We're just wanting to know the ratio. So the ratio of potassium to phosphorus currently is a 3-to-1 ratio. Let's look at what happens with oxygen. 1.88 divided by the 0.471 gives us 3.99. Well, that's close enough where we're just going to call that 4. So when looking at these values, we can get the ratio of 3 to 4. So our empirical formula would be K3PO4. Now, in order to find the actual true molecular formula, we'd have to have the molecular weight of the compound, and there's ways of getting that experimentally as well. Okay, but this is just the steps to get us to an empirical formula. All right, so let's look at an example of where we know empirical formula and we know molar mass, and we want to get the molecular formula. Empirical formula, smallest whole number ratio. Molecular formula tells us the actual numbers of atoms in the formula. So if we have a compound that has an empirical formula CH3 and a molar mass of 90.204 grams per mole, we want to know the compound's molecular formula. So to get the empirical formula, we'd have gone through all the previous steps we did with the mass percents and such. Okay, now we got it to the CH3. Well, this process is relatively simple. If I calculate the molar mass of CH3, I get 15.034 grams per mole. So that's the molar mass of the empirical formula. And you notice the molar mass of the empirical formula isn't the same as the molar mass of our compound. If it was, our empirical formula would be our molecular formula, but it's not. So what we can do is we can take our molecular molar mass divided by our empirical molar mass. So the 90.204 grams per mole divided by the 15.034 grams per mole, and that gives us a ratio of 6. What does that mean? Well, if I take the molar mass of CH3 and multiply it by 6, I get the molar mass of my molecular formula. Which means if I take my empirical formula and multiply by 6, I get C6H18. Well, C6H18 has a molar mass of 90.204 grams per mole. So once I've got the empirical formula, I need to know the molecular weight or the molar mass of the compound of interest. I find the molar mass of my empirical formula, take my molecular molar mass divided by my empirical molar mass, get the ratio, and then take my formula and multiply by that ratio. And then double check it, calculate the new molar mass of my new formula, and make sure it all works out. All right, let's put both of these steps together now. So we have this white powder, we analyze it, we find it to contain 43.64% phosphorus and 56.36% oxygen. We also run an experiment where we determine the molar mass to be 283.88 grams per mole. We want to know the molecular formula of this compound. So, what's the first thing we do? Well, we assume 100 grams of the sample of interest to get the masses of the elements. So if we assume 100 grams, then we have 43.64 grams of phosphorus and 56.36 grams of oxygen. What was the next step? Well, we need to take those grams and convert them to moles. Take the grams divided by the molar mass. We get 1.409 moles of phosphorus. Do the same thing with the oxygen. We get 3.523 moles of oxygen. What was the next step we did? We divided by the smallest number of moles. In this case, the smallest number of moles is the phosphorus. So if I take my moles of phosphorus divided by moles of phosphorus, I get 1. If I take my moles of oxygen divided by my moles of phosphorus, I get 2.5. Now remember, empirical formulas are going to be the smallest whole number ratios. So I can't have PO 2.5. I can't use that. I can't have a 1 to 2.5 ratio. And 2.5 isn't close to 3. The 3.99 in the previous example was close to 4, so we could round it. 2.5, we can't round up to 3. So what are we going to do with this 1 and this 2.5? Well, what we can do to get the fractions to whole numbers is we can multiply by whole number factors. So I can multiply by 2, see if that gives me whole numbers. If I don't get whole numbers multiplying by 2, go back to the original values, multiply them by 3. If I don't get whole numbers from that, go back to the original values, multiply by 4, and keep doing that until I get whole numbers. All right, so in this case, if I take the phosphorus, the 1 times 2, I get 2. Well, any of those that I multiply by 1 are going to give me a whole number, right? With the 2.5, though, when I multiply it by 2, I get 5. So my empirical formula would be P2O5. That is the smallest whole number ratio. That's going to be my empirical formula for this compound, because I can't have a PO 2.5. So now, once I've got my empirical formula, now I want to determine my molecular formula. So how am I going to determine my molecular formula? Well, I'm going to calculate my molar mass of my empirical formula now. So my empirical formula was P2O5. When I calculate out the molar mass for that, I get 141.94 grams per mole. Then remember, I'm going to take my molecular molar mass divided by my empirical molar mass. So my 283.88 divided by 141.94, it's going to give me 2. What does that 2 tell me? Well, it tells me that the molecular formula would have 2 times the ratio as the empirical formula. So P2O5 times 2 would be P4010. So my molecular formula would be P4010. Now I want to check that. I'm going to calculate the molar mass of P4010, and it turns out I get 283.88 grams per mole. So these are some example calculations of where we're getting these chemical formulas from. It's very important you recognize how to calculate mass percents given a formula. You can calculate empirical formula given mass percents, and you can calculate molecular formula. Remember, empirical formula, lowest whole number ratio. Molecular formula is going to tell us the actual number of atoms in that molecule. So get those formulas straight, practice these calculations, and we'll be talking about formulas again here.